Again, welcome to the lab section of today. Today is basically for right now is the focus on the lab, but the topic is still the adiabatic process basically, and we're going to do a process. One of the things I did not mention in the lecture because it's really you can only do so much in a given amount of time, and I know we went too long for that. So let me share with you the screen in here compared to that important point. Because how we're going to do that experimentally, that is really the key when we do physics. Okay. This is where we stopped earlier. So we were describing this process, and it's called an adiabatic process. An adiabatic process or an isentropic process is where there is no heat exchange. Basically, you take a system and you wrap it in a big blanket, okay? And or a thermos, and so that it's basically there is no heat escaping from it or heat going into the gas, one of the two, okay? And then you let it do what it does. In this case, it went from this initial volume to that final volume, and the work is this quantity. It's that area really, and that's the entire energy in this case. So it's energy loss in the gas because of the fact that it went from this temperature, which is clearly high, to this temperature, which is clearly low, okay? From the graph, you can see that this is actually what it went. And we went in this direction, okay? And that is the work, no heat exchange, and that is the entire energy of the gas in this case. The work must be negative. Why do I know that it's negative? Because N is positive numbers, and CV is a constant, and delta T in here is negative because, again, T hot usually is higher than T low, okay? That's how it's supposed to be, at least from this graph. So you might be thinking, okay, how does this, first of all, you cannot do it in an isothermal. In isothermal, the temperature stays the same. And this is not an isothermal. So if we follow the isothermal, you're going to go straight out. You may reach this pressure, but at a later volume. Okay, let me explain this point because it's a very important point, and this has implications on our lab, trying to understand what is going on. Okay. This is the T low isothermal. This is, I'm going to draw them closer because the T high, in other words, the difference between the two temperatures is not that big of a deal. So we went from this point on the PV diagram that has this initial, I'm going to start labeling with 1 and 2 instead of doing that with the initial and final, and P1 into this point where the volume went up to volume V2 and the pressure dropped to P2. I could go on an isothermal instead of following this adiabatic. I could go on an isothermal and reach that same pressure, which is going to happen way back on another volume, V3. So that's the same line in here. But it's going to take this much, basically, process, which is a lot longer process, takes more time to reach the same pressure, but at a higher volume. So an expansion will be much, much higher. Obviously, I will never change temperatures. I will never reach TL because these are isothermals and they never touch each other. The isothermals, they satisfy the condition that PV is equal to a constant, but that constant is actually the temperature times some scaling factors. The point being in here is that this process is rapid. That's why it's called adiabatic precipitation. It happens so fast. So this is a fast process. So if you're doing an experiment, and if something happened rapidly, usually that process is an adiabatic process. That was key actually to Mr. Newton, and we'll talk about this one down the road, in trying to, oh, you probably should have done that in waves. Maybe you did that in waves. When he tried to explain the speed of sound in the air, and he assumed that the process happens at constant temperature, whereas it happened at so fast that that assumption was not correct. So it was really an adiabatic process, where if you guys, which physics you did sound in? Is it physics? Yeah, physics of sound. That was physics 1. So anyway, that is when you come up with a relationship for the speed of sound being proportional to for low, basically temperature changes, it's just proportional, at least the difference, it decreases with temperature, of course, but it changes as a square root of 1 plus something times temperature, okay? And that is actually coming from this process if we do it carefully. But the point I'm trying to say in here is has nothing to do with speed of sound. It's in general, when the process happens so fast, usually it's an adiabatic process. You have to be very careful with that, okay? So when you're doing some experiment and there is heat involved and there is exchange of stuff and temperature is changing and stuff that involves thermodynamics, you have to pay attention to this little detail. If the process happens so fast, maybe you didn't have enough time for heat to be to exchange. The gas expanded very fast or was compressed too fast, then there was not enough time for it to settle so that heat was exchanged. So to a first approximation, you can assume that that's a process that was an adiabatic. And this is exactly what this lab is going to do at some point. So we're going to drop a ball and then we'll have it oscillate. We're going to make the assumption that there is no heat exchange, okay? And that is how we're going to find the angular frequency or the period. Once we measure the period, we're going to measure basically, assuming that this process is adiabatic, we're going to find the gamma value of that gas. Once we find the gamma value, that is really the purpose of this lab. You guys have at least, hopefully you guys have had a chance to read the lab. If not, let me go through the lab instructions. So let me pull the paper, the instructions.
We can't see the lab because we have to do the discussion first, but we didn't get the discussion for today.
See. Okay.
Yeah, it's locked.
I'm
It's
going
locked
to
for me.
I'm going to unlock things. Okay, I didn't know that they were going in that order. Anyway, so let's get into okay, so here is the lab. So this is the lab, the instructions for the lab. The objective is basically trying to pull the properties of the gas using adiabatic processes. That's it basically in a nutshell. This we saw today. PV to the power gamma, where gamma is the same thing as we defined earlier, which is the ratio of the molar specific heat at constant pressure versus that of the constant volume. The molar specific heat constant, Cp over Cv, okay? Or 1 plus R over Cv, however you're going to write it, it's the same thing. And again, this is gamma for a monoatomic gas because of the following. Let me explain why gamma is such and such value, okay? Because it's important to know where those numbers are coming from. Okay, we know for a monoatomic gas that Cv is 3/2 of an R. And we know always Cp is equal to Cv plus R. This we discovered today. So Cp then for a monoatomic gas is 3/2 of an R plus R. The common denominator is 2. And in here I have the numerator is going to be 5/2 of an R. So gamma, which is supposed to be by definition Cp over Cv, is 5/2 of an R divided by 3/2 of an R, and everything cancels. And the only thing that is left is 5/3. So gamma for a monoatomic gas is 5/3 or 1.67. Okay, that's true. Now for a diatomic gas, again, we know for a diatomic gas that Cv has 3 degrees of freedom for translation plus 2 degrees of translation for rotation. So for a total of 5/2 R. Cp is always true, being Cv plus R. Since we know what Cv is, so it's 5/2 of an R plus an R. The common denominator is 2, and it's going to be 7/2 R. So that means that gamma is going to be 7/2 of an R. That's Cp divided by Cv, which is 5/2 of an R, and everything cancels, and it will be left with 7/5 or 1.4, exactly 1.40. So that's for a diatomic gas. For other gases, other systems, usually gamma. For polyatomic gas, it's around 1.3, okay? So this is a polyatomic gas. Because for a polyatomic gas, and I know we didn't get into the molecular structure of the materials, because then what you're going to do, yes, you still have the 3 degrees of freedom for translation. Yes, you still, so basically what I'm talking about in here, something like CO2, okay? That is actually, it has 3 atoms in it. Okay, you still have the rotation around one axis or the other, but you also have the vibrational mode start to kick in. And that actually, in here, classical mechanics fails.
We can't see what you're writing.
I'm not sharing, sorry. Sorry about that. So did you guys follow the calculation in here? For monoatomic gas, CV is 3/2 of an R, and CP is always CV plus R, which means that CP is 5/2 of an R. And if you do the ratio, you're going to find it 1.67, which is a number. It has no units. Gamma is a number with no units. Okay, for a diatomic gas, we saw 3 degrees of freedom plus 2 for the rotation. So CV is 5/2 of an R. So we argued that then CP, which is always CV plus R, is going to be 7/2 of an R. And if I do the ratio of CP over CV, the answer is going to be exactly 1.4. Make sense? And for any other gas other than diatomic or monoatomic, you have to pay attention to these words when you're doing problems, okay? If they tell you that the gas is monoatomic, you really don't need any further instruction. They don't give you CV, or they don't give you CP, they don't give you gamma. So you know what they are. They're these numbers. CV is 3/2 of an R. 1.5 times 8.31, and that's it. And you're going to get an answer. And gamma is going to be 5/2, which is 2.5 times that same number. And gamma is going to be a fixed number, 1.67. For diatomic gas, these are the numbers, which is gamma at the end would be a number with no dimensions. Gamma has no units because it's 2 quantities that have the same units. And this is the units of R, and this is the units of R. So this has units of 1. It's basically a number, okay? But for a polyatomic gas, classical mechanics really fails, because then quantum mechanics and then gets involved, because the energy levels for vibrations are actually quantized, and then we start getting into the fundamental mode and the harmonics that are kicked in. So the number actually is not the same. That is for CV, but CP is always equal to CV plus R. Okay, so in other words, even then, gamma is still more than 1. Of course, CP over CV, and CP is more than CV by the difference of 1, the difference of R. So at the end is going to be always the ratio is more than 1. So this is basically the number that we're going to be using, unless you're given something else. So if you give you a different number, then you're going to. So if I know that it's 1.3, and that is equal to 1 plus R over CV, clearly from here, R over CV is equal to 1.3. In other words, that CV is equal to R over 1.3. Is it? Did I do it correct? 0.3, I'm sorry. What is that? 1.3, because the 1 cancels the 1. So CV has to be more than R. It's always more than R, slightly more than R. Anyway, this is basically some of the information that we know about our systems. Okay, this is very close from a solid, actually, because we have so many degrees of freedom involved. Okay, we're going to get into this aspect later on down the road when we do quantum mechanics. So probably are going to have the discussion. First of all, we're definitely going to have the discussion for the quantization of the energy levels for vibration for molecules. And when we do, basically before we get into solid states and we get into molecular mechanics, so we'll have an understanding a little bit of where these numbers are coming from. But in here, we can understand it in terms of rotation and translation. This is pure translation. This is translation plus rotation. This is from physics 1. We understand what's going on. So we have these numbers. So let me stop sharing the screen and let me go back into the lab. If I can find it, here it is. And let me share the lab, make sure I have it with you guys. And so it's a monoatomic gas. Examples for that are helium, neon, argon, and all of those noble gases basically on a periodic table. Okay. And then diatomic gases are like nitrogen, oxygen, carbon monoxide, and things of this nature that have only 2 atoms in them. Okay. So those are usually the monoatomic gases. Now, water vapor, methane, and also CO2, those are examples of polyatomic gases, okay? So the number is roughly about 1.3. So those are the things that we need to remember for the different gammas. The lab, you're trying to determine the nature of gas based on the gamma that you find in here, okay? Okay, this question, I hope that you guys understand. It says that if a monoatomic gas is compressed adiabatically, to half of its initial volume, by what factor does the pressure increase? Repeat for both diatomic gas and for polyatomic gas. Remember, I'm going to use 1.3 for a polyatomic gas because it's much easier for me to do the calculation. So I'm going to share with you the calculation in here. So we have the gas volume halved. So we want to know the pressure, what's going on with the pressure. Okay. So the pressure must go up. Okay. Why? Let me share with my calculator. Nice paper, actually. Share. So they said this is the volume. It went from V to V over 2. We dropped by a factor of half. Okay. The pressure initially was PV to the power gamma. So this is the initial pressure, must be equal to the final pressure, which is P2 times the new volume. Remember, gamma for monoatomic gas is 1.67, or what is it, 5 over 3. Okay, so all I have to do is find the final pressure over the initial pressure. So P2 over P1 is going to be from this expression, V to the power gamma over V over 2 to the power gamma. Okay, if I do the math correctly. Obviously, this will be 2 to the power gamma times V to the power gamma over V to the power gamma, which cancels. And the answer is going to be 2 to the power gamma. So by how much factor the pressure will increase? It's going to be increasing by the ratio of the pressures is going to be 2, for this case, 5 over 3. So the answer to that is, what is the calculator? Oh, I don't have a calculator. I have GeoGebra, which is fine. I can use it as a calculator also. So hopefully you guys can do the algebra quickly in here. So I will have 2 to the power, open parentheses. I don't need parentheses for GeoGebra, do I? 5 over 3. 5 over 3. I take the cubic root, and then
It's,
so you think, what did you find?
It's 3.17 is what I got.
Yeah, 3.17 or roughly 3.2 times. So it went by more than 3 times. So if a volume drops by a factor of half, the pressure goes by a factor of 3 times if the gas was monoatomic. If the gas was diatomic, I have to do the same relationship, P2 over P1. It's still the same thing as 2 to the power gamma, except gamma now has changed. 7, what is it, 5 over 7 or 7 over 5? 7 over 5, okay? So now I have to go back into the calculator and change the exponent to 7. No, 7 over 5, yes, which is 1.4. Okay. So it did not go by much, does it? A little over 2.5. Correct? or 2.6 times. Is that what you found too? Yes. And for a polyatomic gas is going to be 2 to the power 1.28, okay, which is 1.3. So let me try to put it on my calculator in here, because then I think the numbers start to matter, okay, because if we do a 1.286.
It's 2.4385.
Okay, 2.4, roughly 4. Okay, or roughly 2.4. I mean, it's actually a little bit more, you have to be more. So you see, they go up, but then the difference started to change. It's not as clear as before, okay? So that's the first question. Do you guys understand where the answers came from though? Came from the
Yes.
fact PV to the power gamma is constant, except the V went down by a factor of half, so the pressure must go up to maintain this relationship true. And now what controls this ratio is actually the gamma itself that controls that, the nature of the gas that controls the process. So, and that's if you do the algebra, and if you're careful enough, the pressure should go up, and it is, by 3 times the first time, by a little over 2.5 the second time, and by a little less than 2.5 the third time. But that's really, and when you answer these questions, where is the PDF? When you answer these questions, please try to be verbose. Don't just put the numbers in there. Try to say what I just said, that the pressure increases by more than 3 times, and you show the calculations. And for the monoatomic gas, and by a factor more, slightly more than 2.5, and you push the calculation, you show that it's going to be 2.64, or roughly that number, depending on what kind of a precision you have. By the way, all of these precisions, they're using, what is it? The precision of 3, and it uses 4 sig figs. So you can use 4 sig figs, okay, and use the more accurate numbers in here, because all that is in here is the gamma. So if the gamma is given with the precision of 3 with 4 sig figs, that's probably a good thing to maintain in your calculation. So the numbers I gave were very approximative and not as accurate as the ones that you're going to show, because you have to reflect the data in here that's given to you, since this is a lab. But then in your verbose talk, you can say that for a diatomic gas, it went to slightly more than 2.5 times. And for a diatomic gas, for a polyatomic gas, it went actually by a factor, it went up. In all cases, it went up. It must have increased by a factor that is slightly less than 2.5 times. That's basically how you answer the question. Okay, so let me go back into the screen. So this is what I was talking about. This was given to you by 1.667. This is the number that you can plug in the calculator. And in here, it's 1.400. So that's the number you plug in the calculator. And the number for gamma for a polyatomic gas is 1.286. And that's how you answer the first question. These are the processes we saw today: isothermal, isobaric, isochoric, or isovolumetric, sometimes it's called, or even isometric. The meter is for the distance, and the length or width or height, since they all represent the volume. And isentropic, or the adiabatic process. And the isentalpic process, we're not going to do this in this class at all. And this is process usually for chemistry, and usually they deal with the enthalpy to measure all kinds of properties. Even in engineering, we do that sometimes, but not in this class, okay? So we're going to stop at the concept of entropy. Okay, this is true all the time, PV equal to nRT, or we can use, instead of n, the number of moles, we can use actually the number of particles n, but instead of r, which is a big number, 8.3, we can use kb, which we have seen that r is Avogadro's number times, times kb, yes, okay? So we can push that into the definition of the actual particles in here and rewrite the same expression. This is true. This is how usually physicists write the same expression, okay? But both of them are interchangeable, okay? You can use both of them. Kb is a very tiny number compared to r. And that is because n is a huge number compared to n. Capital N is the actual number of particles, and little n is the number of moles, which is how many of Avogadro's numbers you're talking about. An Avogadro number is of the order of 10 to the power 23. So dimensionally, everything fits correctly. except an N in here has no units at all. It's not a mole or anything like that. And KB carries all of the definition in terms of it's the joule divided by temperature T, temperature Kelvin, I'm sorry. Okay. So here is another question. During an adiabatic compression, okay, compress things, the pressure increases actually, that's what the compression does. Does the temperature increase, decrease, or stay the same? What do you guys think? Just take a guess. So the pressure goes down. That's a compression. And it's an adiabatic process. Okay. That means the volume shrinks. What happened in this case? Does the temperature go up or down? Or it stays the same? Does it stay the same? Is this really an option that the temperature stays the same?
No, it's not an option because you're changing like the pressure's changing. So when something changes, there's another factor that causes it.
Okay, I mean, you have the correct answer, but the reason really needs to be revised, honestly. You have processes where the temperature can stay fixed and the pressure increases. Like an isothermal process is a process where you could potentially, I mean, first of all, isothermal processes, temperature is fixed, but the pressure could potentially increase or decrease depending on what you want. So the fact that the pressure is changing should not be the reason, but you're right in a sense that this process is not fixed temperature because it's an adiabatic process. Since the adiabatic process involved no heat exchange, but you're definitely right, there is a pressure change, there is a volume change, and there is a temperature change too, okay? Because the reason why there is a temperature change is the following. As you compress the gas, the volume becomes smaller and smaller, the pressure increases. So in this case, you're doing work against the gas, so that energy must go somewhere. There is no heat exchange, so it cannot escape in the form of heat. You understand? You have the system inside the thermo basically an insulator, a hermetic system that cannot allow heat to be in or out, but yet you're compressing it, you're putting more energy into it. So where that energy would go, it's going to, I mean, the work is going to increase the energy of the system, so the temperature must go up. You guys understand?
Yes.
Okay, very good. So as long as, let me explain this graphically so that we see what's going on. Let me stop. Let me share. I was not sharing. So here is a gas or a system. So it's general, so it doesn't have to really be gas as long as. Okay, so we have a system in here, and this is a piston, for example, that is sealed from the outside so that there is no heat in and out. There is no heat that can escape, and there is no heat that can come in. But then I'm increasing the pressure. So this piston was here, now it went here. So this is where the gas was initially. Now the gas is actually compressed in here, okay? So I must have done work to the gas by moving the piston this whole distance. So this work, according to the first law, must be equal to the increase in energy because I added energy in the form of work, okay? Because this is an adiabatic process, Q is 0, so there is no problem with that. There is no heat escaping. If the process was not adiabatic, there is a potential that the energy does not change, or the energy can actually go somewhere else too. It can go negative, okay? If in case a lot of heat is escaping as I'm adding energy in the form of work. But since this is a condition, this is an adiabatic process, there Q is 0, so the only way when I increase energy in the form of work is for the internal energy to go up. And if the internal energy goes up, remember, this is an indication that the temperature must go up also. Because this is positive, this is positive. So if this is positive, this one better be positive. Make sense?
Yes.
Very good. So let's continue with the questions. We're exploring them. Okay. If there is a change in temperature, so there is a change in temperature, okay? Temperature must go up, okay? How can this happen if there is no absorption or expulsion of heat? So that's basically what we're doing here. We're compressing the gas. We're making the gas in a smaller and smaller environment. So the average kinetic energy, the path with which the particles start to move decreases, and they get into far more collisions between another, which make them move faster and faster, and that's how the temperature increases. That is the only explanation for it, okay? There is no exchange of heat. The heat is not escaping. The whole thing is wrapped in a big blanket. So for the only thing for this process, so that it's the internal energy must go up, and that's how the temperature is going up. So hopefully I explained it enough so that you can put in your own words in there. Complete sentences. Alish, are you good with the explanation so far? Yes?
Yeah.
No? Okay, very good. So now this is from equation 1. Okay. Okay, let me share with you this. I know I mentioned this stuff. You can put it in this way if you like. You don't have to go follow the steps in here. But let me do this quickly in here. Let me stop sharing. Stop sharing. Let me share with you. Share. As long as you have an understanding of the physics and also the math that is involved, you should be in good shape. So we have PV to the power gamma is constant. So I'm going to call it K1, okay? So we know always PV equal to nRT. Okay, that's always true for the ideal gas. So from here, we can solve for one or the other. I don't know which one is asking, but let's do the TV. So in this case, we're going to solve for P equals to nRT over V. If we sub this expression in here, we're going to find nRT over V times V to the power gamma is equal to K1. So in other words, T times V to the power gamma minus 1 is equal to K1 over NR. And this is what they call K2, okay? Because K1 is just a constant. And now NR are also constant, so that's basically what we have. So this is in a TV diagram, the relationship. T times V to the power gamma minus 1. Remember, gamma is always more than 1. So this number is greater than 0. So gamma minus 1 is always positive. So don't worry about when you integrate this expression or trying to find areas in a TV diagram or something that you're going to get into a problem, you get into trouble. So this is always positive. So yeah, you may end up in the, but you're going to find values that are as expected. So this answers that part. We could go back into this expression and express V now in terms of P. So what I can say in this expression is V is equal to nRT over P and sub that value instead into the first expression. So what we have P times V to the power gamma, and V is nRT over P to the power gamma, and this is equal to a constant K1, okay? Now let's rearrange these things. This is P times a constant NR to the power gamma times T to the power gamma divided by P to the power gamma, and this is equal to K1, okay? We're gonna get into K3 quickly. So what I can do in here, I can raise everything to the power 1 over gamma, basically take the root of the gamma root of this expression. So what I can have in here, I have P to the power 1 over gamma times NR times T over P is equal to K1 to the power 1 over gamma, okay? And from here, it's clear that because gamma is more than 1. So if I take the root, this is going to be less than 1. So it's better for me to write it down in here. So it's going to be T over P to the power 1 minus 1 over gamma is equal to a constant K3, which is equal to K1 to the power 1 over gamma over NR. And this is just another constant, that's all, okay? Gamma is a fixed number. And this is the expression that we're dealing with in here. So for specific gas, gamma is known. Gamma is known. So if we know the gas, we know what gamma is. So this is the expression that I can write it down this way, or if you like, I can write it T times P to the power 1 over gamma minus 1 is equal to K3, okay? So this is basically how you manipulate. So this is your TP diagram. Okay. This is your TV diagram. And the expression we derived in class today was in the PV diagram, which is this one. Okay. As long as you use this expression PV equal to nRT, which is the ideal gas law, and however you use it, you're going to eliminate one of the factors to get to the other one. Okay. As long as you have this understanding, you should be in good shape. Okay. All of this K1 and K2 and K3 are just nothing but constants. For specific gas, that has a specific number of moles N, and for specific gas that you know its nature. So gamma is fixed, N is fixed. That's why these numbers are always fixed in a specific gas that you're running experiments with. Okay. So hopefully, I know you can always come back to this part if you like, and we can go through this one, but it should be self-explanatory. I hope that is enough for you guys. Any questions about this part?
No, I don't have any questions.
Okay, there is a link in the instructions, and it tells you actually, let me share the screen first. The type of experiment that is going to be followed, and the math behind it, and there is a link actually coming from Wikipedia that you guys can further explore to find the mathematics behind it. Once you do the math, you're going to find that this is basically the equation that is satisfied at the end of the day, the oscillations for the ball as it goes up and down. Basically, you drop it, and then as you let it go, it's going to oscillate because of this rapid compression and decompression in the gas, and that becomes an oscillatory mode. All you have to do is find basically the period T. Once you have the period T, you can invert it and find basically what the omega is. So the lab actually will give you what the value of omega is. So once you have the value of omega, you will see that it's related to the gamma, the pressure, the area, the volume, and the mass of the object that falls in, because this is F equals to ma after all, okay? So when you apply that, that's basically how you're going to get this expression. And you sub everything where this is actually becomes like a restoring force, like a mass and spring system. And you find the omega in here. In here, it's just verified that the expression given above for the angular frequency and period of oscillation have proper units. Gamma has no units. Pressure is in Pascal or Newton per meter squared. And this is the area squared. So that's going to be meter. This is the cross section basically squared as it's falling. And this is kilogram, and this is meter cubed. So if you plug in all of the numbers, it should be 1 over second, or radians over second, which is just for the 1 over second. And the T in here is going to have the proper units, which is the second. So test that, okay? And you just plug in the numbers in here. So you should be able to do that. So let's look at that link now, because it's important. We have to get to that link. So I'm going to click on it, and it opened in here. So let me put it on this side, and let me stop sharing with you the screen, and let me share with you the link and how it looks like. Okay. First of all, you can clearly see from this slider, I can change the gas from triatomic to diatomic back to the monoatomic gas, okay? And depending on the numbers that I am supposed to have in here, this is the amplitude X, okay, of oscillations, okay? This is how far you're going to pull the ball up, okay? And you let go of it. Once you let go of it, it's going to oscillate. There is a gas in here. And if you do this experiment in the lab, you have to be very careful in here so that the gas does not escape between the sides of the piston in here as it's falling down. So you really have to do this one very carefully. And of course, people when they first did it, Richard basically So he was very careful with this one, trying to determine the value of gamma, because once you find what omega is, and if you know all of the other parameters like the pressure and the volume and the mass in here that you drop, you should be able to find what the gamma is using that expression that I showed. So again, we're going to go in here. So it's oscillating. So we're going to stop. Oh, why did I stop that? I'm sorry. I'm going to get a recording for the number in here. It's giving me omega 8.25 in here. So I'm going to record that value. Do it again. 8.24, record it in my lab. Stop it. 8.23, stop it. 8.23, stop it. 8.21, stop it. 8.21, stop it. You may need to take a little bit of time in here, okay? 8.25 and so on and so forth. So it's giving me several values for a monoatomic gas. I'm going to do the same thing for a diatomic gas. 7.53, 7.55, 7.53. So is this oscillating between these two values? I think so. Okay. So it's giving me several values. Now let's do a triatomic gas. 7.36, 7.38, 7.36. Apparently there is a flaw in here in this one in here. Anyway, you're going to get several values. Remember, this is a simulation. If we were in the lab, then we will have a better. It's going to be very hard, honestly, if we're in the lab to do this experiment, because of the fact that you have to keep track of 10 oscillations actually going up and down, and somebody clicks the timer, and you have to keep a watch and counting 1, 2, 3, 4, 5, 6, 7, 8, basically until 10, and then you click stop the timer and see how much time, and you divide that value by 10. Now you have t, and then you're going to go and find omega by dividing that by 2 pi. I mean 2 pi over t. That gives you a value of omega, and then you put it in your table. So let me share. What is the share in here? Oh, I'm sharing. Sorry. Okay. You're looking at the PDF file for the lab instructions, or are you still looking at the link for
I can see the lab.
Okay, very good. Very good. So now you go back and report these values in here and find the average, report these values in here and find the average, and report the values in here, report the average. Okay. Once you do that, you're gonna, I'm sorry, once you find the value of gamma, omega, that's what the lab gives you. You need to find gamma using this algebra. So gamma is going to be m times the volume, and you have the volume from the lab, and you have the pressure, and you have everything. So let me go back into those numbers, okay? M is the mass, V is the volume, and A is the cross section, and P is the pressure. Okay, and they tell you exactly what these values are. So let me go back into the. It's not there. Sorry about that. So the volume is 8.2 liters. Make sure you use a metric cubic meter. Okay, 1,000 liters is a cubic meter. The pressure is 1,014 millibar. Okay, and you can vary the pressure to see the effects of the pressure. Okay, and for that, you are going to have a. You have to convert it into a Pascal. Okay, if you're going to use the metric system. So 1 bar is 100,000 basically pascals. So you have those conversions, and the amplitude is given to you there, so you can use that. And the omega is given in radians per second, so the omega is good. So you have to use those expressions in here, and the mass is given to be 10 grams. Okay, and what else is changing in this expression in here? We have the volume, we have the pressure. We have everything. So we should be able to find what the gamma is for the different gases. And that's the one that we have average. And this is the one that we average, and this is the one that we average. Now, you're supposed to find these numbers. If you don't find them, That's fine, because the simulation is not perfect. Actually, simulation is, even if we did the lab in person, actually, you will find a lot of errors because of the fact that the gas is escaping, and it's really not easy to control lab if we do it this way. There is another lab actually we have on campus for the value of, for the adiabatic process. And actually that one also is not really easy to control, but you can control that one better than this one. Anyway, effects of the volume. In this part, we explore the effects of the volume, change the diatomic gas, and change to a diatomic gas. So when you go back, slide the slider to a diatomic gas, and use the average value found above. So use this value for gamma that you find in here, okay? Because that reflects more the data that you have in that lab. And change the value and fill the data in table 3. So we're going to change the volume in here. So we're going to control the volume and then go and find the value of omega that is given to us by the expression, and square the value and put it in here. And once you have the volume in liters, make sure you write 1 over volume is going to be in cubic meters. So you have to convert 1,000 liters to a meter. In other words, divide this number by 1,000 and invert it. So we're going to go back into this expression in here. This is what we're trying to plot. We're trying to plot omega squared as a function of 1 over v. Obviously, it's going to be a line. It should be a straight line. When you square omega, it's going to be omega squared, because that's what the lab is giving you. And you're changing v. So this becomes your independent variable, is 1 over v actually is your independent variable. And omega squared is your dependent variable. So this should be a function. Omega squared is equal to a constant times 1 over v. So it's going to be a line. The slope of that should be gamma, which you already measured from the previous step, times p times a squared over m. But you already have these values. So you would want at some point to compare that. First of all, it's a straight line. And second, that the slope matches. So that's basically how we're going to calculate this. So we're going to plot this one. It should be a straight line that passes by the origin. It should pass by the origin. If it doesn't pass by the origin, that's fine. That's part of the error, okay? So you're going to have that part of your error. And use your favorite method to use a linear fit. So in this case, you can go back to Excel, put the numbers in Excel, and do a linear fit, which should give you the slope. And the slope should really be exactly gamma times p times a squared over m, and compare the two and see how well your fit is and how well the theory matches the experiment. And that's your lab. Now the conclusion depends on the errors that you get in here, the errors also you get in here, which you need to report, and explain where the errors are coming. I mean, even if it was a real lab, you will have a lot of errors in it. So this is not outside of the realm of the possibility. Furthermore, this is the fact that this is just a simulation, not the actual lab. You guys understand what's going on? At least for the entire lab, but what we need to do?
Yeah.
Yes.
Okay, so as I said before, normally during lab sessions, what I do is I will stop the recording, then I leave the session on. So if you guys choose to stay working on it then here, that's fine. If you leave and finish it later on, that's fine. So that's basically where we are. So I'm going to stop the recording, and it's up to you guys if you want to hang around, or you can leave and finish it later on at your own time.
Are you able to unlock it so that way we don't?
Yeah, I will. I will right now. Okay.
Yeah.
Okay, let me see what's going on in here.
Everything is locked for me.
Everything, did you do the, hold on, why is it?
It's
I
locked
like
until you. It's
Yeah,
locked
I
until
haven't,
you do it in order.
Hold on.
Yeah.
It has to be done in order,
that-
you're right.
Yeah. Wait, could you remove the system? Like that puts it in order?
Yeah, there is a discussion item that is the one that is blocking this one in here. Can you refresh the window and let me know?
Yeah, I'll try it. It's good. It unlocked it now.
Okay, very good. So I'm glad that you guys are here. So let me stop the recording.